Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. My name is Paul Abernathy, and welcome to our podcast. On today's episode, we are going to talk transformers. Of course, I have a video series out there on transformers that I encourage you to go watch on our YouTube channel. You can get there from our website at masterthenec.com. But we've got a lot of requests to do some basic podcast on the subject, and hopefully not get too deep. In other words, since transformers to me is a very visual topic, when we're doing a podcast, I have to keep it as simple as possible in order to be able to paint a mental picture without you physically seeing anything. And so we try to make it as simple as possible in order to be able to convey that message. But if you've listened to any of our other podcasts, you kind of get that message already. And so let's just go on and get into the topic so we don't end up having a 4-hour podcast on transformers. So what are we talking about? So today we're going to look at the difference between the delta-delta and delta-Y transformers. We're going to talk about the basics as far as the relationship between the primary and the secondary. We're going to dabble a little bit about turn ratios, kind of give you what you need to kind of know. Again, this is not an engineering thesis. You are trying to help you understand the basic concepts of transformers. Maybe you're trying to take an exam. Or maybe, you got to remember that when we design these systems, the engineer designs these systems, as an electrician, you and me, when we're installing them, we're simply picking out the transformer that's specified to be able to get the job done. Whatever the VA desires are that we need in order to handle whatever our load calculation has been configured at, we're going to search for the transformer that we need. Now, transformers come in VA, KVA, excuse me. And so, again, KVA is just a KVA times 1,000. That's going to tell you what the VA is, and you're going to need to know that when you're doing a lot of the calculations to calculate the primary current rating or the secondary current rating of a transformer. So a couple important things to remember before we get into the relationships is transformers, again, are rated in kilovolt amperes, KVA, but they're actually sized in VA rating of the actual load that's being supplied. So the engineer, or if you're the designer, you're the one that's going to figure what is the actual load that I need to be supplied by this transformer, because you know what? It's not an indefinite amount of power from a specific transformer that you choose, okay? You're only going to get it, and that's why we need to know the calculations to be able to calculate primary and secondary current ratings of a transformer, because there's only so much you're going to get out of a transformer. So if you undersize that transformer based on the load you need, then that could be a problem. One, you're damaged the transformer. Two, you're not getting out the necessary amount of power from this transformer as needed due to the design. So it'd be a poor design. Now, many cases we will oversize a transformer for future expansion. There's nothing that says that I can't have multiple secondaries coming out of a transformer as long as that transformer is sized properly. So a lot of times engineers will size it a little larger than necessary in order to compensate for expansion or whatnot. Again, if you don't use all of the potential of this transformer, that's perfectly fine. It is better to be sized appropriately or oversized to meet future needs than it would be to be undersized or be too restrictive in its use. Okay? So kind of remember those things when you're designing for transformers and whatnot. And sometimes you'll see that it's not that much difference to go up to a little larger KVA transformer in order to accommodate expansion or things that you're not accounted for in your load calculation. Okay. So anyway, primary. Let's talk about line. So on any transformer, let's talk first about a delta to delta. Okay. So we have line 1, line 2, line 3 coming into a delta on the primary side of a transformer. Let's say that's 480 volts. And then we want to do what's called a step-down transformer, where we're going to step it down to 240 volts. Okay, so let's say we just have a pure delta secondary with no grounded neutral conductor. It's simply line to line. It's going to be 240 volts. It is what it is. Line 1 to line 2, 240. Line 2 to line 3, 240. And line 3 to line 1, 240. Okay? Theoretically, in a transformer, even a delta-delta or delta-Y, Doesn't matter. It is called line. It's the line in. And then, of course, contrary to many people's belief, you also will be line out of the secondary. So that's actually going to be the line in to electrical equipment, like your panel board, switchboard, whatever it happens to be. So when we think about it, it makes it easier for us to understand this relationship. The line 1, 2, and 3 coming in is usually in a transformer marked H1, H2, H3. Okay, and then the secondary is usually L1, L2, L3, that type of thing. Not to be confusing, but both are considered line. Now, when we understand this, it helps us kind of learn some basics, some things that we need to ingrain. Now, it doesn't mean you have to remember them forever. You just need to ingrain them in your mind and remember that the line, primary or secondary circuit conductors, are theoretically considered line. Okay. Now, people argue that it's load, but what is the load? There is no load. It's a line in, and it's the line coming out that goes into the line side of the electrical equipment. Okay. Now, you can argue until you're blue in the face. It doesn't matter. You won't change my opinion, so why worry about it? All right. Now, line current. How do I measure line current? Or what is the relationship of line current of the ungrounded conductors? Of course, you remember, and we have ungrounded conductors, these are your hot conductors, and we have grounded conductors, which are the ones that are intentionally connected to ground, okay? And of course, we have equipment grounding conductors, we have supply side bonding jumpers, and we have all those other types of conductors, which we will probably maybe not touch on in this podcast, but we do have a video series. I encourage you to watch it to get all the aspects of grounding and bonding and all that kind of stuff. But right now, we're going to talk about the ungrounded conductors. That's the hot conductors. So, line current. It's a pretty simple formula that you're all probably real familiar with. And that is line current for single-phase transformers, or in general, in order to calculate line current, it would be VA, which is the volt amps, okay, divided by E. And, of course, E is the voltage. Of course, if it's single-phase, it's just one voltage, okay? It should be line, whatever the VA is, or the kVA converted into VA, divided by 480 volts. And that's your line current. Now, if it's three-phase, how do you do that? Well, remember, it's three-phase, okay? So the square root of 3 is 1.732. So if we're trying to find a single line current, then we have to do a little bit of math first inside of some parentheses. And that is the voltage times 1.732. Now, remember back from our video, I gave you some shortcuts to remember. You can skip one little step here by remembering 3 specific numbers. If you're dealing with a secondary, let's say, or whatever the line current is you're dealing with, if it is 480, then just remember 831, okay? So it would be the VA divided by 831 if you're trying to find the line current for a three-phase. If it's, say, 208, then what you're going to do is that's going to be 360. So it'd be the VA divided by 360. Again, that is the value of 208 times 1.732, okay? And that's what's going to give us the value of 360. All right, so that's just a shortcut. And of course, if you're dealing with a 240 volt application, then it would be simply 240 volts times 1.732, which is 415, and you're going to use that value, okay? You really can drop off the decimal points at that point because it's really, for real, a practical sense, it's not going to make a difference for your application. So that's how you're going to determine line current on, and it doesn't matter either side, but that's how you determine line current by using those type of formulas, okay? All right, so give you an example. Let's see. In a delta configured system, we're talking a delta now, the line current is greater than the phase current by a factor of 1.732, which obviously 1.732 is the square root of 3. So if I had 100 amperes and that was my line current, or I had measured my line current, okay, then I do that, divide that 100 amperes by 1.732, and that gives me 57.736. I'm going to take that 6 and round it up to 57.74. That is my phase current. If I know my phase current on an exam, it gives me my phase current, and it asks me what the line current is on a delta system, then I'm going to take 57.74, okay, and I'm going to multiply it by 1.732, and that's going to give me 100. Of course, it's going to be 100.00, so it's just 100. So you see the relationship in that is the line current doesn't equal the phase current, okay, in a delta system. All right. Now, if we're thinking the same concept, take it a little further, let's look at a Y and how that would function. Now, if you're familiar with the Y, is where the delta is unique because the winding is connected end to end, okay, and that forms the delta. Okay. Whereas in a Y configuration setup, it's slightly different because the Y, each one side of all of the windings of a Y configuration are connected together, but the other ends of those windings or that single phase transformer are not, and that's going to be your line 1, line 2, and line 3. But they're connected together at one center point, and if you think about it, it literally looks like a Y configuration. Okay, I mean, in reality, that's exactly what it looks like if you visualize the concept. Okay, all right. Now, there's all types of calculations we can do at that point, but calculating the line works the same way. But when we're calculating the line current, you have to remember that in a Y, it's simple. The line current equals the phase current. Not the same for the delta, but it is the same for a Y. So a line 100, if I were to take a measurement across the winding on a Y and try to get the current, it was 100 amps of current. Then that I should get the exact amount on the line conductor as 100 amperes because they're center connected. All the transformers are connected together. Remember, a Y is made up of 3 single phase transformers as well. And so when it goes through that winding, it's ultimately going to be connected to that tap at the end or that terminal at the end. Let's say it was in a Y configuration. Let's just say that it's the C leg. That even if I measure on that conductor, since it's connected to that one side of that single transformer, it's going to be whatever the current was on the line, whatever it was on the phase is going to be the same as on the line, okay, and vice versa, okay? All right. Now, when we hear the term from, that's the concept of line current. Now, when we hear people say line voltage, okay, which is different. Line voltage, which does change in some cases depending on the transformer, in some cases not, and this is important to remember, is that the voltage is between 2 ungrounded conductors. Okay, that's the difference. So line voltage is different than line current, but in line current, remember that on a delta, line current does not match the phase current, but on a Y, line current matches the phase current. But in a line load or line voltage, it's a little different. The delta, the line voltage matches the phase voltage. However, in a Y, the line voltage does not match the phase voltage. Okay, so easy to remember that is when you're dealing with the current, the delta, the delta. Well, if you want an easy way to remember the Y part because that's the one that's different. Y, remember that the Y on a line current is phase equals the line. The Y on a line voltage, the line does not equal the phase. Okay. However you need to remember it, that's the concept. So let's look at an example. If I have a delta configuration, it's a 240 volt, and it's a line, okay, and I'm going phase to phase, then I get 240 volts. All right. Well, obviously, if I'm measuring the line from line to line, I'm going to get 240 volts. If I'm measuring the phase from A to B or whatever it is, I'm going to get 240 volts, okay, based on that winding, okay? So that doesn't change. Now, in a Y configuration, because they're center tapped at the middle, and what I'm going to get in that case is if I had 408 volts on the line, then the actual phase of the winding is going to give me 120 volts, okay? So just remember that the line voltage is greater than the phase voltage by a factor of 1.732 when you're dealing with the Y configuration. Okay. So in reality, even if I had, let's say, a delta to delta with a delta high leg, I'm going to measure across the phase voltage. Then if it's a delta to delta, I'm going to still get phase voltage is 240 volts. And my line voltage between any line to line is still going to be 240 volts. That's not going to change. Okay. Now, if I have a measurement in one of those high leg configuring, and when we say high leg, that is where you have a delta secondary where the C winding, in this case we'll say phase, is center tapped in order to derive a 12240 volt out of that delta secondary. And then you have the B phase, which is traditionally and required by the code to be identified as a high leg in that type of setup. If you measured from the high leg or the B leg over to the neutral, then vectorially you're going to get a 208 volts. Okay, and that is your high leg. Okay. Now the current that flows on the transformer winding, again, if I were to take a measurement of the current, and I measured it from a phase on a delta, that is going to be different current than what I have on the line. Okay, it's going to be different. Okay, just remember that. If I'm dealing with the voltage on a delta, okay, the line voltage, then the line voltage is going to match the phase voltage. Okay, and again, if I'm doing this with a Y configured transformer, slightly different. The line current is going to be equal to the phase current. Okay, no difference in there when it comes to the current. However, when we're dealing with the voltage, that's different than what we're dealing with current. When we're dealing with the voltage on a Y, the line voltage is going to be different than the phase voltage. Okay, hopefully I've hammered that home. Okay, and in our scenario of how we're dealing with those type of layouts. All right, so it's important to talk about configuration and how it's distributed onto a transformer when we're putting various loads on it. So we'll kind of just we'll touch on that. And so that we understand that when I say phase current, that's the actual current itself that is flowing through that transformer winding, that specific winding. Okay. When I say phase load, on an exam or something we're discussing, then that's actually the VA load. That's the actual load that's on that transformer winding. Okay, and so it's really important to understand how you make the configurations on how you hook up these various loads, because it's really important that we balance out transformers properly. Real important when we're dealing with a Y configured transformer, because you only have the three legs that are only going to provide you with 120 volts on each of the actual windings of a transformer. So we got to look at how this is laying out. Now, let's just talk three-phase for a second. So if I have a delta three-phase load, let's say I have a motor, and it has 18 kVA, so it's an 18,000 volt amp load, whatever the load might be. And I hook this on a transformer. Now, basically, that's going to be, if it's balanced out, a load, we're going to assume the load is balanced out, and that's placed on a three-phase 240 volt delta transformer, then basically a third of the line load is on each one of the windings. So in an 18 kVA, then I'm going to have 6 kVA on one winding, 6 kVA on the other winding, and 6 kVA on the other winding. Okay, so it's going to balance out. Okay, it's an 18 kVA load source. All right. Now, if I'm dealing with a motor that's, say, a 10 kVA, and it's single phase, and it's being derived from a three-phase, all right, and that is a single phase load, and again, maybe it's just a single pure 240 volt, two conductor line, one line two load, and it is 10 kVA, then what you're going to get is 100% of that load is on that winding. Okay, so that 10 kVA is that one transformer of those three single-phase transformers that are configured in a delta configuration is going to handle 100% of that 10 kVA. Obviously, it's not going to balance out or distribute amongst any of the other phases because it's only connected to the aspects of, let's say, line A and line B, and that's it. So that's a single-phase 240 volt. 100% of the line load is going to be on that one winding. Okay? Now, what if it's a 3 kVA single phase 120 volt and we happen to have a transformer that is actually a center tapped C phase in order to give us a derived neutral point, which is going to give us that 120 that we need. At that point, just remember that half of that winding, that half midpoint back of that C winding is handling 100% of that line load. So that would be that 3 kVA or 3000 VA. real important when you start balancing out transformers that you start thinking about that you have each one. One of the fallacies that people don't understand is transformers have a kVA rating, but you have to understand that it is made up of 3 individual transformers in a configuration. So you're only as strong as your transformer, this individual transformer. Yes, they're put in configuration, but if you overload one transformer, you imbalance the system, you can create problems. And so it's really important to analyze it, okay, and see how you're balancing these things out. So you really, if it's a 3-phase and you want to know it's 18 kVA, you just simply divide that by 3, and that's what it's going to be equally distributed among each of the windings of the 3-phase delta transformer. And you saw how we did each one of those and how it works out. Now, conversely, let's look at what it is when we do the phase load for a Y transformer. Okay, all right, and so now remember we're dealing with a Y, and so we're going to get a 280 volts. So typically, what you've got is a 120 280 volt Y secondary transformer. And let's have the same loads because it makes it simple for us to be able to work this. So when we talk about phase load on the Y, we're literally talking about the phase load on the actual transformer windings. Okay, they're going to be the one doing the work here. Okay, and so if it's an 18 kVA or 18,000 VA, then it's the same scenario. You're simply going to divide it by 3, and that is going to be the distributed kVA on each one of the windings of this transformer. So it'd be 6 kVA on one, 6 on the other, and 6 on the other. Okay, and that's how you're going to do the aspect of it. Now, what if we're trying to get, again, single phase, okay, aspect of it? Well, if you're only going to take single phase from the windings of a Y secondary and you're going to line 1, line 2, then you have to be real careful because it doesn't necessarily equate to an even exchange of 5 kVA on one winding and 5 kVA on the other winding. What you're going to get out of that configuration is potentially more current that travels or is being imposed onto that winding. And so that takes more consideration to understand what you're doing when you're trying to take a 208 single phase from a Y connected transformer. Okay. Now, but in the shortest term, I usually tell people this. Depending on what you're dealing with, is take your kVA, okay, divide it by 2, and I tell people as a cautionary tale. It might not work always, but a cautionary tale is take your kVA, divide it by 2, and add 2 kVA to it, each winding, as a cautionary tale if you're designing it. Now, that might not always work out, but it is a comfort zone for things that are 10 kVA up to maybe 15 kVA and less, whereas you are not going to have the issue of tearing up, let's say, the winding because you overcapacity the winding, okay? All right. Now, dealing with a Y phase loads on a 120 volt, pretty simple. In this case, we have the center tapped Y, so we're able to derive our neutral at the neutral point on the center point of the actual transformer winding. Typically, it'll be marked as XO. And what you'll have is you'll have a neutral, and then you'll have one of the legs to A, B, or C. Okay, and in this case, just remember that winding is literally handling 100% of the load. No different than we did with the Delta single phase 120, except for it was only 1/2 of that winding was actually handling that load. So important to understand that because it's very easy to overload a C transformer configuration in a Delta because you overload the either half or either side of your actual winding with the C winding, C1, C2, because that can cause you problems. Now, what's the beauty of a Y secondary? Why would somebody use a Y secondary? Because you're able to get 120 volt loads and you have 3 transformers to allow you to dissipate that. The downside is you're dealing with 208 volts. Okay, but if I had a building that had maybe a Delta coming in it, and at some point I had the lighting system, and I might want to go to a transformer that takes it from a Delta down to a Y configuration in order for me able to get a 208 120 panel board that's going to allow me to distribute the lighting loads more evenly across all of these transformers. And I have 3 transformers that I can distribute and get 120 volts for my lighting and things like that. If you have more motor loads, then you're probably going to want to deal more towards the delta configurations. And that's typically what we're going to see in really high commercial aspects where they need those motors and they need that full winding versus needing more 120 volt loads. That's where you're typically going to see the Y configuration for the 208 120. It doesn't mean that you can't get 208 volt single phase out of it. You just have to take some things into consideration to remember it. Because at the end of the day, you have to understand that the phase load on a single phase 208 is the phase current times the phase voltage. Because they're actually out of phase in their relationship based on the windings that are inside of it, the value will always be larger than the result obtaining by dividing the line load by 2. Okay, so if you're simply trying to divide it by 2, like we said, that's never going to be the case because of the internal windings. You need to go a little higher in the consumption. So what I say is usually if I'm dealing with a 15 kVA or less, then for ease of calculation, I simply take whatever my value is divided by 2 and then add additional 2 kVA per each winding. And that's how I consider it when I'm sizing my transformer for that aspect of it, or to make sure that my transformer can handle it. Each one of the individual single-phase transformers in that configuration can handle it. You get what I'm saying? I think you do. All right. So that's what we're talking about when we're doing it, kind of distributing it from a load perspective onto a transformer. Okay? So I think you get the concept of where we're going on it, that when you're dealing with the 120, that it literally is handling 120. It's literally handling all of the VA, okay, on that winding. All right? I guess at this point, it's good for us to talk a little bit about what this concept called a turn ratio. What is a turn ratio? Well, if I have a 480 volt transformer to a 240 volt secondary, so I have a 480 primary, and it states on the nameplate that it's a 480 to 240, then that is literally a 2-to-1 ratio, okay? Because the primary is twice the amount of the secondary, okay? So if it's a 480 primary and a 240 volt secondary, then what I've got is a 480 to a 240. That's 2-to-1. Okay. If I'm doing that with a, let's say I'm dealing with typically what I have in a delta to a Y configuration is I'm going to have, let's say, a 480 volt primary and I'm going to have a 120 208 secondary. But you measure phase to phase in order to your ratio, because that's the turn relationship that you're dealing with. So if it's a 480 208 120, then it's basically a 4-to-1 ratio. The one winding is 120. So 480 is 4 times the rating of the secondary winding, which is 120. Okay? We're not dealing with what we're getting line-to-line values. Okay? We're just talking about the ratio of the turns. Okay? So it's, again, one phase as it relates to the primary, as it relates to the secondary as far as the windings go. So that would be like a 4-to-1. Okay? So very common aspect of how we do it. Again, we've talked about this, or maybe we didn't talk about it, is understanding the relationships between the different turns and what we've got in the turn ratio. So primary side of a transformer, typically you're going to have more turns, okay? But it's going to be smaller wire because it's going to be lower current, but it's going to be higher voltages, 480, okay? Whereas the secondary is going to have fewer turns. Again, it's the ratio. And it's going to have a lower voltage, obviously, because we're trying to go, for in this case, let's say 480 to a 240, whatnot. It's going to be higher current, and it's going to result in higher current. It's going to tell us what? Immediately, we know we need larger wire, okay, on that secondary. So we have a primary to secondary, and it's all based on the number of turns, okay? And we kind of rehashed that and went over it a little bit in order to get a full understanding of this turn ratio concept. So typically what we'll see in a delta to delta will be 480 to 240. And again, that's a 2-to-1. If we see a 480 to a 120, which is typically what we're going to get on a delta Y configuration, if we're going 480 to 208 120, is what we're going to get is a 4-to-1. So that's how you would depict it if you ever had that on an exam or whatnot. Okay? All right, so hopefully that kind of explains turn ratios. And again, it's the number of turns on the winding on the primary versus the number of turns on the winding of the secondary in order to achieve that. You're not dealing with line to lines here. We're talking about the turns of the windings of the actual transformers itself. Okay? All right, so I guess the next thing we probably should talk about, because we did talk about a little bit about balancing, we did talk about turn ratios. I guess for a podcast, we should probably talk about that neutral current and what happens in the neutral current, or that connection that's made at the neutral point. Again, what we're dealing with is the unbalanced load, and that's what the neutral current, that's what the neutral is going to carry. It's going to carry that unbalanced load. And again, we're talking about what's on the secondary grounded conductors, okay? The neutral, okay? That's what we're talking about. We don't have a primary grounded conductor that's brought to this side. We only deriving it from the secondary, okay? So that's what we're talking about. Now, unbalanced neutral load. Let's talk about how you configure that when we're dealing with a delta, because you need to understand that the neutral current that is being generated by this unbalanced load is actually calculated by subtracting line 3 current from line 1 current, because that is the one that you're going to have the connection within the windings in order to achieve that center tap. Okay, so that's what we're doing. So it's, in order to calculate that, it's just simply the current from line 1 minus the current from line 3. All right, and that's how we're going to determine what our neutral is, our unbalanced neutral load. Now, good, you got to know what your currents are. You have to know what your VAs are. You have to calculate everything out. But that's the formula that you would typically use in order to determine the unbalanced neutral load for a delta secondary. Okay, and some things to remember also, that when you have a delta, let's say you have a 122/40 volt system. If you have a secondary that is 122/40, that is a delta with a center tapped between line 3 and line 1. That's typically the C winding. In order to derive 120 volts from the line 1 and line 3 to the neutral, you're going to get 120 volts. Okay, and that's typically what you see coming down into your home or something like that. If you go from the leg B over to the neutral, it's not really a neutral. It's a grounded conductor in that scenario, because it is not even amongst all lines. So that would be 208 volts. Therefore, you have no neutral loads are connected onto the 208 volt line or the B leg. Okay, it's not done that way. The resulting voltage, because of the way that it vectors out, you're going to only have 208 volts, and again, that is not going to be usable in our case to give you any line to neutral loads for 208. Okay. All right, now the same relationship, I guess we need to talk about is the unbalanced load, and this one gets a little more complicated. There's a formula. I tell people, don't get involved in memorizing so many formulas. Just write them in your code book. Know where to find them. Check with, if you're taking an exam, not typically the kind of question that's going to come up on the exam, because there is so many points in there that you could screw it up. But at the end of the day, you want to write the formula in your code book if you're the one doing the design and you're dealing with this, because it can be a bit of a complicated formula to try to remember. Because it deals with a lot of parentheses that you have to solve, a lot of brackets you have to solve in order to come up with what's called the neutral formula for the Y secondary. All right, but we'll talk about it and kind of give you the formula. So the formula itself, and again, trying to visualize this for somebody, is where you have the square root of the the current from line 1 squared, plus the current of line 2 squared, plus the current of line 3 squared. So you solve that first, okay? It's in parentheses. Minus, then you have to solve the second part of that, which is minus, and you have what's called brackets. And you have to solve within each of the parentheses within the brackets. So that minus line 1 current times line 2 current, plus line 2 current times line 3 current, plus line 1 current times line 3 current. And you put all those values in there, and then you're going to add those three together, the values between the current of line 1 times line 2 plus the current of line 2 times line 3 plus the current of line 1 times line 3, add them all three together. Then you take what you did on the first half of the equation and you subtract it from what you had on the second half of the equation, and then the square root of that. And that's going to be what your actual unbalanced neutral load would be for the Y secondary. Okay, people know me for wanting to not pass up on examples, so let's do one. And it's obviously a small one, so I just want to give you an example. Let's use this formula and let's go on and do a Y. Obviously this is going to be a small one, but let's go on and do it because I think it's important for you to understand it. So the formula is, again, square root of current line 1 squared plus current line 2 squared plus current line 3 squared minus the line 1 current times line 2 current plus line 2 current times line 3 current plus line 1 current times line 3 current. Okay, and then once you fill in, you solve it down through the brackets down, then it's just the square root of whatever the value is of the first part between the minus whatever the value is of the second part. So let's do that. So let's say I had line 1 is 25 amps, line 2 is 28 amps, and line 3 is 30 amps. Okay, and what you're trying to do is simply find an unbalanced neutral load for this Y secondary. Okay, well, it's not complicated. You just got to remember that you have this formula. And once you have the formula, it's really simple. In fact, it's probably, of all of the engineering calculations, this is probably one of the most easiest ones because you just simply fill in the blanks, right? So in our case, it would be the first part of the equation would be 25, because that was line 1, squared, which is 625. You write that down. Plus it says plus line 2 squared, which was 28 squared, which is 784. Plus line 3 squared, which is 30 squared, which is 900. So you add all those together, it's 2,309. So you write that down. That's the first part of your equation before the minus symbol. Now let's add the second part. So the second part is current on line 1 times the current on line 2. So in our case, it was 25 times 28, which is 700. Okay, forget my math if it's off, but I think it's right. Okay, the next one, and you write that down. The next one was line 2 current times line 3 current, which was 28 times 30, which is 840. Okay, you write that down. And then 840. Then the third one was, it said line 1 times line 3, which was 25 times 30 amperes, because that was what line 1 was, 25, and line 2 was 30. That's 750. Okay, now, remember that portion of the equation? It says you just add all those three up together. So it's 700 plus 840 plus 750. That's 2290 or 2,290. So now we have the first part of the equation, which is 2,309, minus the second part of this equation, which is 2,290. Okay, now, ultimately that equals 19. But the easiest way to do it in a calculator is hit the square root and then square root symbol, and then put in 2,309. Minus, and then the second part, 2,290 equals, and you're going to see that's 4.36 rounded amps. So that is actually the unbalanced neutral load. Now, you probably could have looked at that and said, okay, well, it's only 25, 28, and 30, so that I know between these, I probably could average it out. But if you know the formula, it's just simple. That's telling you what your actual neutral current's going to be, okay? Or the unbalanced, I should say. The unbalanced neutral load in that. And it's simply using that formula. Okay? We are going to talk about that in the grounding and bonding X segment on my video of transformers. We'll have that formula on the screen. So if any of that was confusing to you, I encourage you to watch our video dealing with the calculations and things like that for transformers. It's a 6-part series. And it kind of covers everything from cradle to grave with transformers. Okay? All right. The windings of a transformer. These are the coil-shaped conductors that wrap around the core. And those are called the windings. But most of the time, and when we're talking about it, that's also when we say phase. So when we talk line, we're the conductors that connect to the actual phase winding of a transformer. But when we say winding, we're synonymously saying phase as well when it comes to dealing with transformers, okay? So the winding is called a phase. Is certainly how we're going to depict it in all of our discussions and how that works, okay? All right, now, Y-configured transformers. We talked about deltas. Again, the Y-connected transformer is one where each of the three windings or each of the individual single-phase transformers are connected at one common point, and that is the center point, and that's what creates this shape that looks like a Y, okay? It's also a Greek symbol, but we all are familiar with Y, okay, in the alphabet, right? That's what it looks like. It physically looks like a Y configuration, okay? And then each of the lines 1, line 2, line 3 connect to the end of each individually of each winding. Okay, and in a transformer, you'll typically see that as line 1, line 2, line 3. Okay. Also remember again that both are lines, but on a transformer, usually the primary side, which is a higher voltage, is going to be H1, H2, H3. That is to give you a better understanding on how to make those connections within the transformer. The only difference is typically on a transformer where it's a step down. You're going to have a secondary, you're going to have one more termination, and it's that center point for the neutral, and that's going to be your XO, okay? But you might have transformers, like I said, a delta secondary that does not have the configuration in order to center tap the C winding. So really, that transformer will just have an A, B, and C, and it will not typically have an XO connection on that, okay? It could have a corner ground. It could be a corner grounded delta scenario and things, but that again, each transformer is going to be different. So just make sure you look at them and you understand how that works. Typical single phase transformer, the kVAs for single phases, at 7.5, based on the formulas, that we would use, the shortcuts when we know 208's 360, 240 is 415, and 480 is 831. But remember, when you're dealing with single phases, you don't need that 1.732. So you simply take the values. So if it's a 7.5 kVA, then it's 7,500 divided by 208. Okay, and if we do that in our math configuration, then what you're going to see is it's going to give you an ampacity value. So 75,000 divided by 208 is going to give us 36.05. Okay, so just 36 amperes is all you need to know. All right, same thing whether it's 240. You just simply take the kVA, convert it into 7.5 times 1,000 or whatever the value is. It doesn't matter whether it's 10 kVA, 15, 25, 37.5, whatever it is. You just take the 37.5 times 1,000, and that tells you it's a 37,500 VA. And you simply divide that by whatever the current, whatever the voltage rating you're dealing with. So that divide that by 480, for example, is going to be 78.125. You can drop the 1.125. It's 78 amps, okay? Where when you're dealing, again, just remember in three-phase, whatever the kVA rating is, simply take the kVA, multiply it. So it's 15 multiplied by 1,000. That's going to give you the VA value. And remember, those little shortcuts. At that point, you're going to divide that into, if it is 208, you're going to use 360. If it's 240, you're going to do 415. If it's 480, you're going to do 831. If you don't remember that, just remember that it's whatever the voltage is times 1.732 because you are dealing with three-phase. Okay? So that's kind of all you have to remember when it comes to that. Now, primary, so we're talking delta to delta transformers. Again, line 1 to line 2, 480 volts. If we're talking a 480 to a 240 volt delta. Okay, so it's a step down transformer. It's a 2-to-1 ratio. So 480 volts, line 1 to line 2 is 480. So what is it going to be across the phase windings? It's also going to be 480 because remember, line voltage equals phase voltage on a delta. Okay, now what about the secondary? Okay, interesting. Line to line voltage on a secondary of a delta, if you remember, is the same as the windings on the phase voltage on the delta. However, if we do have a transformer that has a center tap, okay, and that connection is being made from line 1 to line 3, then you are going to get a phase reading or neutral voltage of 120 volts, okay, to line 1 to neutral, And in line 3 to neutral, you're going to get 120. But in line 2, you're going to get 208. So just remember that aspect of it. And how do you get that high leg? Again, you just simply take the voltage and do it times 1.732, and that's going to give you the 208 voltage. Okay, so that's how you get the 208 voltage on a 120, 240 volt secondary. Okay, remember that is called a high leg, wild leg, whatever you want to call that leg. It's got to be identified in accordance with the National Electrical Code. If it's a color, then you're going to use orange, but orange isn't the only way to identify a delta high leg in a system. Your authority having jurisdiction may have a allowance for you to use labels, marker, a marking system, or whatever you want to do to identify it. Okay, they might allow that. Okay. All right, I'm coming up on 45 minutes, so I'm going to have obviously multiples, but we're going to keep this one pretty short, and we're going to do another one, and we're going to talk about what's called a delta current triangle and how to use this triangle, something you might want to jot down. We're going to talk about some other examples in calculations and how you and how you do some readings. And we're also going to dabble a little more into what's called Y transformer balancing. We talked a little bit about it when it comes to balancing out the loads, but as a design wise, we're going to the next podcast, we'll kind of talk about balancing out Y transformers so that we don't burn them up. In other words, we distribute the loads evenly across the transformer to keep it as balanced as possible. Okay? All right, so that's enough for this one, guys. Hopefully you got something out of it. Obviously, we're going to have additional podcasts on the Transformer series. I encourage you to go watch the videos on our YouTube channel. You can get there by going to our website. You'll see there's a link at the top to our YouTube channels. If you haven't visited masterthenec.com, please do. You don't have to go around on the social medias and click the like buttons. We don't really care about that. You don't even have to subscribe. We're not into worrying about the number of subscribers because our data, our analytics show that we're getting thousands and thousands of watches, and I track everything. I know who is on where and when at any given time so that we can see which shows are performing better, which ones the people like, and things like that. The liking it is just a bonus, and I appreciate it. But I know that I have got thousands and thousands and thousands of people listening to them and watching them, and that's all we're about. We want you to be able to watch it. If you get something out of it, great. If you don't get anything out of it, or you think, wow, that's too basic for me, then here's a tip for you. Don't watch them. Don't listen to them. Hey, I'm not out here to convince everybody. Okay, I can't train people that are not willing to listen or don't want to learn. Okay, but there's a lot of people that do want to learn. So that's the people we're targeting. So at the end of the day, God bless, stay safe. And again, visit our websites, visit our Facebook pages, things like that in order to help you better understand the National Electrical Code. And stay tuned for another podcast where we talk more about transformers.
Every day the future's getting closer. Every day the future's looking bright. Every day is another beginning.